Hello, this is the video for topic 5.1 acid-base concepts part 1. In this video, I would like to talk about introduction of acids and base. So the first understanding or the context of it, acids are compounds or ions that donate protons, whereas bases are compounds or ions that accept protons, which are H plus ions. So let's go through that. So traditionally, based on the definition of acids and bases were based on how they behaved. So for acids, sour tasting was the property that was believed to beat acids, and it somehow corrodes metal. Whereas bases, they derived from the word alkali. I think it's the Greek word or Latin word, which means calcine ashes, so plant ash, which gives slippery feel when it's in solution form, as well as it neutralizes acids. So when you pour something sour or lemon juice or vinegar into ashes of plants, they somehow neutralized. Current definition though is developed by or established by Laurie and Bronsted. Here's a picture of them, and it is based on a proton transfer. Proton is H+, we'll talk about that in a minute, but for acids, in Laurie and Bronsted definition, acids are something that can donate proton, H+, whereas bases, they are substances which can accept proton, H+. Now here's a link for a video, so if you have access to this lecture notes, click on it, make sure you watch it. Now, in terms of reaction, when acids are placed in water, they increase the concentration of hydrogen ion, which are protons. Now, you might wonder why it's called protons. Now, that's due to the atomic structure of hydrogen. Now, hydrogen has got one proton because it's element number 1. And one electron is naturally there in one atom of hydrogen. But when it loses that one electron that was there and becomes hydrogen plus, so hydrogen ion, what's actually left is one proton, isn't it? And that is it. That is it. So it's called proton. Hydrogen ion is just a proton. However, it is highly reactive and it don't want to be on its own, so in water or solution it bonds with something else, so it doesn't exist. Protons don't exist as on its own. Okay, so protons have form the hydronium ion, so instead of existing as H+, it forms hydronium ion, which is with a formula of H3O+. So, for example, if you are to write the equation for water and proton, which is hydrogen ion, you can write H3O+, which would look like this is something else for later. Water itself is a liquid. H+ doesn't really exist, but you can still say it's an aqueous because it used to be part of the acid solution and now increases the amount of hydronium ion. Okay. Now, within a hydronium ion, what's happening in that is that oxygen atom is contributing its electrons, electron pair actually, to form a bond between oxygen and the proton. Now, it is called coordinate bond because electrons are only shared from one side. So this occurs when electrons shared only come from one side of bonding atom. In this case, oxygen. So oxygen is the only thing that's donating its electron to make a covalent bond. Here's a diagram, but I'll go through that with you. So, coordinate bond. If you have got H2O, well, let's just use the this electron diagram. So if you have water and one of the non-bonding pair of electrons attacks a proton from an acid, so that pair will attack this positively charged particle, proton. What will form is that HOH, extra electrons here, extra electrons here. Oxygen itself has 6 electrons, and hydrogen brings its own electron. So H2O on its own had octet. All the atoms in there had an octet, very stable configuration. Whereas H plus, which became a part of this whole thing here, would bring in an extra positive charge. And as you can see here, the electron pair is only shared by one side of the bond. So oxygen is the only thing contributing to make this bond happen. This bond here is called the coordinate bond. So if I use lines to show bonds, as a normal convention, an arrow is used to show that the electrons are shared to hydrogen and only one way. And the bond here is the coordinate bond. And when coordinate bond happens, what it there you go. So arrow pointing at the coordinate bond, which is shown with an arrow from oxygen to hydrogen. Come on. Okay. This not only occurs for water, but also ammonia and nitric acid, or nitrous acid even. So let's just draw them too. So in case of ammonia, well, if it's usually just a ammonia and H3 with non-bonding pair of electrons sitting on top. But if it gains a proton, what will happen is nitrogen is the only thing donating its non-bonding pair of electron, so it forms a coordinate bond between nitrogen and hydrogen, NH4 plus that is. This can happen in nitrate ion, which is NO3 with 1 minus. Now, NO2 itself have got well, nitrogen can make 3 bonds and oxygen can make 2 bonds. So this atom has got 1 bond and 1 electron to make a bond, and 1 electron here to be able to make another bond to something else. Usually you would see a double electron here, so non-bonding electron pair. But the pair of electron can be used to make a bond between oxygen. So then you will have NO3 with a negative charge on top on this oxygen. So as a whole, for nitrate ion, you will see this kind of configuration. Why does this become coordinate bond? Well, that's to do with octet configuration. So what's stable for each bond, each atom? Nitrogen wants to have 8 electrons, and that's it. Nitrogen is in the period 2, so it cannot have expansion of octet. It cannot accommodate more than 8. So 1, 2, 3, 4, 5, 6, 7, 8 from on its own, and that's it. Whereas this oxygen didn't really mind having 2 extra for the 6 electrons that it brought with it. So oxygen will also here have 8 electrons, and it's happy. So by making donation, a one-way donation of electron here, both will achieve an octet configuration. If oxygen donated 2 bonding electrons to nitrogen, it would have overclouded electrons with electrons for nitrogen, even if oxygen still had 8 electrons around it. So this is a bit more stable configuration for nitrogen and oxygen atoms here. Now, if you're looking at HNO3, it would look like this. If it was HNO2 instead, this is HNO3. So nitrous acid instead, you would be looking at H or N, double bond to oxygen, and non-bonding pair of electrons still sitting there. All right. When coordinate bonds occur, they cause what's called ionization. What you could see up here, or this one, is exactly the case. So occurs, this ionization or dissociation occurs when acids and bases are added to water. So acid was added to water. Acid was added to, in this case, it's a base. And there are 3 examples that I would like to write down. So here are those 3. First one is hydrochloric acid and water, ammonia plus water, and lastly nitric acid and water. So let's write those equations down. So hydrochloric acid and water. So HCl, and if you add that into water, coordinate bonds will occur between this hydrogen here and this oxygen here. So you will have Cl minus and H3O plus. It's very hard to get 100% pure acid because it usually comes in solution. So that solution is added to pure water. CO minus still dissolved, and H3O plus existing within the solution here. Next, ammonia plus water. Ammonia again, same thing. It's very hard to get 100% ammonia. May be possible in the industrial world, but not in a household or laboratory setup. So I'll go with AQ, so solution of ammonia. Now ammonia can accept proton, so that's a base. So base is added to H2O. What's going to happen? The ionization occurs because nitrogen can cause a coordinate bond between this hydrogen. That'll be the proton. So you will have NH4 plus. Ion is dissolved, and left over of the water molecule, that is OH minus, hydroxide ion. Finally, another acid, nitric acid into water. That's the nitric acid. If you put that into water, same thing will happen. This hydrogen gets donated, makes a coordinate bond with water. So you will get NO3 minus plus H3O plus. So dissociation or ionization happened. H and NO3 dissociated, made into ions, so ionization happened because coordinate bonds can occur between water and hydrogen.